Alright, it's time to move on. Uh, let's get started. So, some little reminding of what we was doing. We are currently implementing the test ROMs from nesdev.org. And we have covered the basics of the 6502 CPU processor, and we are currently implementing the instructions that are specific for the NES console. So this is a good moment to be around. So right now we are using this little file as documentation, and we are deleting the instruction while they are implementing them. Let's put it around here. Okay. And the way we are going to choose what to implement next is just running the test case. And when we see an instruction that is not implemented, we pick that one. So now it's turn for opcode 227 decimals. So we have to open the calculator and find out what is that number. 227, it is the E3, the famous E3 or the infamous E3, depending if you can attend or not. So let's search what is E3. Where are you? Search result. Here we go. So it is ISC, increase memory by 1, then subtract the memory from accumulator. So it affects the 0, negative, overflow, and carry flag. It's an interesting instruction. So it is increase, subtract, carry, maybe? Or increase, subtract, I don't know what is the B. So let's go to our NES CPU and let's add this instruction to the bottom. Let's copy one random line and repeat it. ISB, I think it's ISB, but we can check it really easy. Invalid hex notation character X. What is this error? We don't have it in here. In string OX. So we have a couple of mistakes around. So where are you, OX? Oh, it's probably this one. That doesn't make much sense. I don't think it is that one. Okay, I need to start searching again. So, where are you? How can I find this mistake? What is producing you? I assume I need to find it, but there is not causing a mismatch. Could it be this? Are we just connecting the observer? No, it is not being connected. So we can try to remove it and see if it still... Okay, it still creates the output, but made less. The assertion happened in a different place now. No, it's the same assertion. So function hex to int. Oh, that's interesting. Do I have an int like this? Use string hex to int. Returning 0. Where could you be? It doesn't sound likely to be this. So it's interesting when I remove that. It still shows the error even before the start of the application. What? I will eventually find what it is. For now, I will undo what I changed. So every time I make a change, it parses again and prints the error. So whatever it is coming from here. So where do I have an OX? Or maybe it is not exactly because of that. So something that has happened from the previous time we worked was that I upgraded to Godot 4.1 stable. So maybe this is just new. And we have two options. We can debug it in the C++ code, or we can just ignore it for now. I think we can try the latest and see if it becomes too annoying. Because it is annoying, sorry to complain. Anyway, let's move on. So, if I don't see you, it doesn't matter, right? Increase memory, decrease register. And we are having addressing mode, and we are having a register. Yes, we don't need binding. You can just use this way. name of the register A, and then the addressing mode. So let's duplicate this. 1. So this one has 1, 2, 3, 4, 5, 6, 7. And I have 2, 3, 4, 5, 6, 7 instances. So first one is E7 and F7 EF FF. We found the bottom instruction. Yay! FB E3 and F3. And the addressing modes that matches are 0 page, 0x, absolute, absolute x, absolute y, indirect x, and indirect y. Okay. So now for the size and cycles. 2 byte, 2 byte, 3 byte, 3 byte, 3 byte, 2 bytes, and 2 byte. That's all. And now the cycles. First is 5 cycles, 6 cycles, 7 cycles, 7 cycles, 8 cycles, 8 cycles, and I did something wrong. Okay, it was 6 twice. Hey! What's up? Trust me, I am a developer. Looks like the automatic bot did not like that you was writing in all caps. So you can try again without all caps. And what is still failing? Ah, probably that it doesn't exist, this function. Function. Yo, I am awake. I was doing my 3D renderer. Oh, that's awesome. So, trust me, I am a developer. Couldn't you find a shorter name? Anyway, he's working on making a 3D renderer for the Game Boy Advance console. He's not streaming, but I am following his project, like personally. I am sure he's having fun. So what was the order for this? It was first the register and then the addressing mode. I think that was the case. Register and addressing mode. So this one is at least interesting. So it is going to increase the memory and subtract from the accumulator. So it's like transfer 1 from the accumulator to the memory. But my question is, are these the flags related to the accumulator or to the memory? By the way, I found a bug in the snake game. The fruit sometimes can be gathered in the space occupied by the snake. I was going to fix it, but I got lazy. What? That is a bug in the game, not in the emulator. Because the game does not check if the snake is occupying the space of the fruit when locating it. So what you have to do as a gamer is don't hit yourself, so move somewhere else so your tail moves out of the fruit before you can collect it. So what happens if we call increment memory with addressing mode by -1? No, sorry, it's by 1, it is incrementing. And then decrement register or increment register be register by -1. That should update all the same flags. Okay, it doesn't update carry and overflow. That's not good. So inks ini text day. So how should this work? Let's just give it a shot and fix the bugs later. Okay, it's time for fixing bugs, I guess. So we implemented ISB and we was supposed to increment the memory and decrease the accumulator. But why the hell did it jump from 40 to 53? How did that happen? So I am wondering, maybe I did the wrong assumption in the order of arguments. So let's pause and see what happens. Oh, you subtract the memory from the accumulator. Okay. So increase the memory, then read the memory. Address equals, it was get operand address, the addressing mode, value, and equals to memory memread address, and now we want to decrease by minus value. Is that it? So we wanted 53 and we ended up with 3F. So yes, it was the opposite to my initial idea. So I think this is more or less what is meant to be. So we got closer now. So memory was 45x. Oh, it was indirect. So 47, 06, 47 EB was the value. So it should be 40 minus EB. Hex 40 minus EB. And it is 55. I wish I could change this to be 8 bits. Can I change that somehow. Configuration. Why are some stuff in Spanish? Oh, I can make it dark. Thank you. So beef shifting, arithmetic, logic. Bah. Increase memory by 1, then subtract memory from accumulator. Memory from accumulator. Yeah, that I think this is correct. With borrow. So instead of beating my head against the keyboard, I think I will just search for the example and find out what is this meant to be. So it was FF, maybe? Yeah, it is probably not. Okay, ISB. So data is self increase of code. What is inc? Function increase. So it takes the addressing mode, reads the data, adds 1, writes it back, updates 0 negative, and returns the data. So it is doing what I think it is doing. So it's what I am doing here. I am increasing the memory by 1. So it is starting the same way. And then it is subtracting data from register A. Exactly the same I am trying to do. But my function seems to not be doing the right thing. So what does this function do? Data as signed 8, wrapping negative, wrapping subtract 1. So this seems to suggest it subtracts value plus 1. This seems to suggest that. So what does this happen then? Okay, now the value of A matches, but the program counter is not matching, and that is because we are not updating overflow and carry. So I think the way to solve that is, instead of calling this, I will copy this and make an equivalent application that takes care of carry and overflow. So I think in these two cases carry should be set. Is it? Or is this overflow? When is carry meant to be set? I always confuse those. So let's see when is flags.b involved. Update b flag. And b flag is updated. Update c flag. I see. So the result you set for update b flag, is it already clamped? No, it is the unclamped result. So that means I need to do the negative operation the right way, I guess. And let's try this. Update v flag. The previous. No, what was PA and PB? It's so frustrating. What does this do? Add to register. Function add to register. Okay. So that's why. That's why it was adding one more. Insert, remove. Maybe I have to, instead of increment register code, decrement or subtract with carry to register. Okay. Addressing mode. Can I use the addressing mode instead and not use this? How does that work? Okay, that worked pretty much fine. So the error I am having seems to be because I messed up something in the definition. So this is the FB. I have FB in here. And I am using absolute X twice. And that is the reason why it is failing. So now we have ISB implemented properly, which is awesome. Let's add that to the repository. Git add. Yes. Yes. No. Yes. Git commit. Implement. How was the wording we was using? Illegal instruction. I always mistype this. Anyway. git commit. We have no. Implement iLiga ISV. Increase memory, then subtract to accumulator. Instruction. Right. Git push origin main. And with that, we got rid of this. Next instruction. So the instruction is 3. Let's search 03. And 03 is this SLO. Shift left 1 bit in memory, then OR the accumulator with memory. Okay. So let's hide this a little. The output is not complaining because we are not opening this. So whatever error we are getting, it happens on the parsing of the GdScript. So as long as we don't need to change this file, it seems to be not complaining, and that is cool. So this one is SLO. SLO. Remove the opcode. Let's change the function of the name. Shift left memory, then or logic or register. And we are going to use the A register and the addressing mode. Okay. And we have 1, 2, 3, 4, 5, 6, 7 instructions. 1, 2, 3, 4, 5, 6, 7 instructions. 07, 17, OF, 1F, 1B, 03, 13. And we have 2 bytes, 2 bytes, 3 bytes, 3 bytes, 3 bytes, 2 bytes, and 2 bytes. Awesome. And this one is 5 cycles, 6 cycles, within at this column, 6 cycles, 7 cycles, 7 cycles, 8 cycles, 8 cycles. Okay, cool. And now we have to update the addressing mode, which I believe it matches this one. 0p, 0x, absolute, absolute x, absolute y, indirect x and y. So yes, it matches all these. Copy. And come here and paste it. And now we can implement this memory. Func shift left memory and then OR, logic OR. Register and addressing mode. So now, can we do left shift shift, logical shift right, shift left memory, then arithmetic shift left. So the right shift is logical and the left shift is arithmetic. Okay. So we want the one on the memory. And we are going to pass the addressing mode. And now we want to the logical, no, or register, inclusive or exclusive, or with register. I think it is inclusive. P register and then the addressing mode. And the answer to this is run and see if it works or not. Okay, we got directly in the NES failing instruction without any print. So no failures. That worked out of the box on the first try. Awesome. Give me a second in the other monitor. Okay. So let's commit this. And yes, we added SLO. We added a new function. And I don't want to include this. Git commit. Implement illegal SLO shift left memory then logic or with accumulator instruction. Git push origin main. So these instructions are, most of these instructions are just combinations of simpler instructions. Okay, next. So the next opcode is 35. If we look at the calculator, 35 is 23 in hex. So let's find it. Which one are you? Here you are. So you are rotate left, then and the accumulator. Okay. So this one is RLA. Duplicate one line for reference. I wonder, what if I do this? And then change all of them at the same time. Will that help? RLA. It takes the same number of bytes, 2233322, and cycles are 5, 6, 6, 7, 7, 8, 8, exactly the same amount. So this one, let's change shift for rotate. Rotate left, then logic and to register. Register A and same addressing mode. 0 page, 0x, absolute, absolute x, absolute y, indirect x, indirect y. Perfect. So now we have to choose write the opcodes and we are done with this. 27. 37 2F 3F 3B 23 and 33. And now we just have to implement this function. Register an addressing mode, copy paste, and now this is rotate left memory. Rotate left memory with the addressing mode. And now we have and bitwise and with register. So we pass the register and the addressing mode. And if we are lucky, that will be all. Famous last word. And indeed, that worked out of the box on the first try. Awesome. So let's commit that. Git add import. Yes, yes, no. Git commit. Implement iLiga rotate left accumulator. Rotate left memory, then logic and with accumulator. Awesome. Git push origin main. Small commits. That's the clue. So, next instruction 67. Decimal 67. It's hex 43. So we finished this one. Let's delete it. And do I see 43? Yes, I see 43 with my own eyes without having to search it. If we are lucky, we are going to finish the entire document today. Anyway, so this is shift right and then exclusive OR. What strange combinations of instructions. Let's close this for now. So this is 1, 2, 3, 4, 5, 6. The same 7 addressing modes. So let's just copy this. Oops, I did something stupid. So now let's change this to shift right exclusive OR. Shift right exclusive OR. Let's delete the opcode and the size are the same. 22333 22. The number of cycles are the same. 566 7788. Okay, so now this is shift right memory, then exclusive or register A and addressing mode. All good. Only the opcodes are missing. 47, 57, 40F, 50F, and 50B, 43, and 53. Okay, awesome. And now we have to implement the actual function. So I think I will put it in here so the two shift functions stay together. Copy the arguments. And now I need to call shift right memory. Logical shift right memory. With the addressing mode. And then exclusive or with register P register P addressing mode. Cool stuff. If we give it a run, it should run in the first try. And it did. No unmatching line. That is so cool. Oh, we are ready to commit it. Yes? Yes? No? Git commit. Let's change this one. So this one was. Move this a little. You move as well. SRE shift right memory, then exclusive or with accumulator. Awesome. One less. So, who is next? Next is 99. Who are you, decimal 99? You are hex 63. Do I see you? Yes, I see you in here. You are rotate right. And then add to the accumulator. I wonder what was the idea behind the combinations of logical and shifting. There should be some connection of why those was joined together in the same instruction. There should be some mathematical operations that are made that way. I multiply by 2 and then add it, or something like that. They should have some meaning. So it has the same 7 instructions, so I will just copy this. Paste. And this one is RRA. Remove the opcodes. Rename to RRA. This is rotate right. Memory, then add to register. Okay, and register and addressing mode is correct. Zero pay, sorry, size is 2233322. Cycles are 5667788. So this is all correct, and I only need to update the opcode 6777 6F 7F 7B 63 and 73. Save. And what is next? Now this is called rotate right and add. So function rotate right and add is the same two arguments, and let's call rotate right memory, and then add to register or increment register. Increment register. No, it's not right. What was add called? Transfer, subtract with carry, logical, inclusive, or add with carry to register. This one. Be register, and then the addressing mode. And now we got some unmatches. Interesting. The matching is happening on instructions that are not new, they are not added now. AD. But the reason could be that the memory is not matching because of what we have done last in this memory stage. So we are storing A into the memory, and this was the value before storing. Not after. That can maybe make sense. So we could be doing something wrong. So it's ignoring a lot of memory address. That's fine. Anyway, quick check. How far have we gone into the log file? We're in the 8,900, almost 9,000. Wait a second. We're almost there, actually. Holy moly. So we seem to have a mistake. But we are almost there, indeed. So this memory was meant to be FF, but it's not. So are we doing something wrong with this? So let's see. Pop up. So the value we are writing is 82. And we are going to add 82. Is that right? Yes. To value, and we are doing 178 plus 82. Decimal 178 plus 82, and that is 264, which is an overflow. Oh, and it's even one more because of the carry. That's 105. So the value stored is 05. Wait a second. Is that so? I did something wrong. 261. 261 is 105. Why is the value of the register 82? P register value value is 5. It is just not updating this. Okay, I was worrying for nothing. So let's do this. Let's see when is the memory changing, the memory that we are finding unmatching. So let's continue running. Move on. And now the memory that is matching is 4015, 44, 45, 46, 47. So let's use our magic observer to see when the memory is changing. And the memory range is 4006 to 4007. Run. Okay. Wait a second, it did never. It did never change? Did I do something wrong? I connected to write memory, to write mem, and it should have printed this, but did not. What did I do wrong? Did I mistake the memory? I think not. Let's try this particular one. 4015. 4015. And what is the print? It's just print rich, and we can now use a color orange. Color so it's also strange because that memory is ROM memory. Maybe we even get errors in here about it. So what is memory? This hex 4015, and it is 6405, and it's this one. So this is why we are not getting the emission of the observer. So let's emit the observer. Address. From memory starts. So what is this range? From memory starts at 8000 and ends this. Okay, so we don't have this. So, oh yes, I think it was the ALU. I think it was even mentioned in here. Remember, the test room should drive your progress. In the end, the CPU should support 256 instructions, considering that 1 byte is for the operation code. We have exhausted all possible values. Finally, the first mismatch should happen on this line, which is indeed the line that we are looking at. Almost at the very end of the NES test log file. That's good sign. 4015 is a memory map of the APU register, which we haven't implemented yet. So that means that we can ignore this for now, and let's see what we are going to make. Yes, let's remove this. We don't want to emit anything. And I want to go to the debugger and remove this breakpoint, because now it is causing trouble for us. Okay, awesome. So we have two instructions after the end of the file that doesn't exist in the log file. NES log, I want to see the log file. and the 91 matches RTS. Yes, it matches. And 92 and 93 doesn't exist, basically. So this is simply awesome news. So basically I think that means that all these instructions are not tested in the ROM test file. So we are going to just implement them without a way to test. I think we added this. Git add. What do we have changed? Oh, we did not implement we did not commit RRA. So yes to this, yes to this, no to this. Do I want to add this? Probably not. Let's not add it. Let's go to the commit, and this was RRA. It was rotate, write memory, then add with carry to accumulator. Push to main. Cool stuff. So now, how do we know that this is going to work? And byte with accumulator. If result is negative, then carry is dead. This is quite easy, I guess. So what I am going to do for this is implement them in the way I think they are and compare it to the example in Rust in here. I think that should do. So let's add ANC, I suppose it's called. Oh, it's actually AAC according to this. But we was using this before, but this one says AAC. ATX, ALX, LXA. Stop the program counter. Wow. So let's look at this. We have our processor. Let's redo this. I want to see the processor, how many instructions it for. The CPU has the instruction set of 231 instructions. So yes, we kind of need those. So let's do it. Let's keep using these as mnemonics, the ones that are between parentheses. I simply don't know what what is supposed to be used, so I will use that one. So this one is immediate. Both are immediate, both are register, and both are logic and with bitwise and with register. Yes. That's it. Bitwise and with a register. And this is Ank. And then sets the negative carry. So it's bitwise with register with carry. That is the difference. Okay, I understand. So it is OV and 2B. 2 bytes, 2 cycles. Function. Bitwise ANS with carry. So we got bitwise and with register, B register, B addressing mode, and then if flag negative is set, flags carry value is set. So the idea is, if it is not negative, I don't change it. So if it was false, I keep it false. If it was true, I keep it true, unless negative is set. I think that is the idea. Let's do all of them together. So this one is R. And byte with accumulator, then rotate 1 bit right in accumulator and check byte 5 and 6. Okay. And then rotate. And rotate right. That is the meaning. And let's duplicate this. R. It is the 6B. Bitwise and register. Sorry. Then rotate register with flag. with CB flags. It's a weird instruction, but the important is it takes little cycles. So I suppose this has a very specific meaning or very specific reason to be called. So it seems to be some kind of optimization for some hardware operation that is very common, I suppose. So this is immediate, sorry. Register uses A and the instruction is take B. So everything is ready here. So function. And we want this. And byte with accumulator. Bitwise and with register. The register and addressing mode. Then rotate 1 bit right the accumulator. So rotate right register, the register, and we are going to check 5 and 6. Bar 5 bool equals to 1 2 3 4 5 6 7 8 1 2 3 4 5 6 this one. I am doing it dumb, but I just want to make sure I do it correct. E5 equals 6 equals 1. Is that valid? I suppose not. And 6 equals 1. Let's make sure it works the way it is intended, because otherwise it is like an invisible parenthesis here and it is saying if true equals 1 or if false equals 1. Flags C value equal true and overflow is false. What is wrong here? What 5? It's 5. If they are both 0, it clears both. What is the error now? Okay, it's true, not 0. if 5 and not 6. If 5 and not 6, then set B and clear C. And then if not 5 and 6, set C and set B. Oh, set both. If only 6 is set both. If only 5 is set C and B. What? Oh. Set B and clear C. Okay, set B and clear C. Okay, this one. If both are 0, then clear both. If both are 1, then set C. Okay, should be correct. Famous last word. We have no way to test it. So add byte with accumulator, then shift right 1 bit in accumulator. So this is basically the same, but without the weird flags. And shift right and rotate. Oh, it was rotate and this is shift. Okay, that was the difference. What I am doing? I did something wrong. Okay. Let's see what is already implemented. Okay, Anc is already implemented and R is already implemented. Awesome. Save. Next is ASR. Let's just copy it. And this was is 4B. And shift right, bitwise I, then shift, register, function, argument, so now it's bitwise and with register, p register, p addressing mode, and then shift right, shift right register, p register. Okay. Done. And byte with accumulator, then transfer accumulator to X. Opcode.new. What I am doing? Once again, I should just duplicate it. ATX and transfer X and transfer X. Code is AB. No, it's not AB. Oh yes, it's AB. I mistook A and 4 because they are similar. That was a little stupid. 2 bytes, 2 cycles, bitwise, and then bitwise, and with register, then transfer to register. So this one is going to bind the 2 register. And I am going to not specify any register. And we'll make the addressing mode there was a non-addressing? Yeah, I think this is the way to do it. Func. So we have the AND register and the transfer register. Bitwise, and oh sorry, it was immediate actually, not no addressing. I was mistaken. Bitwise AND with register, P AND register, and then transfer register from 2, P AND register, P transfer register, and this one needs the addressing mode that I did not specify in the arguments. Okay, awesome. And X register with accumulator, then and the result with 7 and store in memory. What? What is the logic behind this? So let's see what is this. Let's see AB. I forgot I was supposed to do this. XAB, and it is loading. from the opcode. So it is not making an AND operation, it is just loading. And then transferring to X. But wait a second, AB already existed? No, XAB did not exist. And then what is this? LXA. Oh, this is the name, LXA. I got scared. I used the wrong name there. ASR, correct. And ARR. So what did I do wrong now? Let's see. ASR. It is 4B. It is different. To what the description says. What does the other documentation says of it? So this one, let's move this here. 4B. ALR. Yes, this naming. Equivalent to AND. Then LSRA. So this one says to AND, not load. What does other sources say? For B. So ALR. So this is 4B ALR. That's not nice. Attributed sound uses these instructions. So it does not give descriptions on what they do. How about the other one? ALR A equals A and memory, immediate, divided by 2, so that is the shifting. That is what the shifting means. So yes, it is indeed and this is wrong. I suppose. Do I trust myself? No. So what does this source? This one? This is the one that has descriptions. So what is AB? $AB? ATX? No, it is not even mentioned. Maybe with OIL? Not? LXA? It's not even mentioned. Okay, this I already did this one. So this is an AND with accumulator, then result with 7 and store in memory. So let's find it in the Rust code and see what it does. It gets the memory. Yes, it's absolute Y. And then makes an AND. What? But AX absolute Y and indirect Y, and it uses X register in the AND. Mem address 8 and store in memory. I see. Mem address shifted by 8. Why is addressing the memory? So memory address is 16 bytes. So it's taking the higher byte for the AND. It's so strange. Do I have another description of this? 9F? No? 93? AXA Cha. No. Not even mention it. And this one, AXA J 9F. Okay, here is 9F. So address equals A and X and H, but doesn't say what is H. And it's AHX, which is not listed in here. So I suppose H is the high of the address. So it has a node with the number 1. Can we find this? Unstable in certain matters. Is anyone making use of this? Is this anywhere else? I think I will wait. I will not implement this one. Maybe none of them except maybe kill. But is kill even used by any game? The data bus will be set to FF. I don't know exactly what is the data bus. Anyway, let's do that. KLI. No, sorry. KIL. It's 1 byte and 0 cycles. Kill. And it's non-addressing. Maybe I can just use quit. Is running equals false. Did I re-implement it somewhere? No. Okay, so this one seems right. So it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So all of these uses a 2 in the end, and we have 0, 2, 1, 2, 2, 2, 3, 2, 4, 5, 6, 7. We don't have an 8. 9, no A, B, no C, D, no E, F. So we have kill instruction. And memory with stack pointer transfer result to accumulator, X register and stack pointer. I will not do that. So what is this? From here. So get the address, get the value, add it to the stack pointer, store it into AN register, updates the stack pointer, and updates 0 and negative. So it's pretty much straightforward. How do you describe this? Add memory with the stack pointer. So do you have a description for this? Or an equivalent? No VB. Do we have lar? No. Lai. Las. Where are you? Ah, last. Okay. We don't have you here. We have lar. Las and lar are the same. Las. Okay, we have a last in here. It is B. API times 4. So AX and S equals address to S and S. Okay, so let's go. Let's name it load and stack. That is the meaning of the wording. Last, and it's BB. Load sorry. Bitwise and memory with stack, then load registers, and we are going to bin an array of registers. And this is indirect, sorry, absolute y lar. Func and then an P registers, which is an array of registers. This was parentheses. And the addressing mode, so strange. Bar address equals it was operand, sorry, get operand the addressing mode bar value equals memget, sorry, memory memget memread, sorry, address bar result equals value and stack pointer why is this? Oh, it's missing the colon. For reg in P registers, so we also want to do stack pointer equals result. Stack pointer is just an integer, right? Yes. Reg.value equals result. So we set the stack, set the two registers, and now we have to update 0 negative with result. Did I miss something? I think not. No? So this one is gone. Wait a second. Almost forgot. It is 3 bytes and 4 cycles. And X with the high byte of the target address of the argument plus 1. Store the result in memory. Extract exact operation unknown. Read the referenced documents for more information. So I think this one will be more descriptive in this table. So if I search DB, so this is the meaning of each column. So it's immediate. So x equals to a and x minus the immediate. So what happens first, the subtraction or the AND? Oh, I'm looking at the wrong one. It's this one. Okay, the subtraction happens later. So A X X bitwise and register, then subtract. This one is taking A and X, and this is the immediate. And the opcode is TB. It takes 2 cycles, and it's called AXS. Okay. It's strange. P and register. P store register. Store or load? It's called load, I guess. Register 8-bit. P addressing mode. Addressing mode. So we first bitwise and with 2 registers. So the register. How does it work in Rust? Let's see if I can find. So it gets first the value from memory. the addressing mode bar to subtract. Sorry, I am forgetting to put type hinting, memory, memread address, and makes an AND of the two registers and the result. It updates carry. If to subtract is less or equal to AND result, flag carry value equals true. Update 0 negative from result. And then sets the load register. Okay. It's and the result. Okay. Makes sense. One less. So 9E. 9E address is going to be equal to X and the high value of address. And this one is absolute Y. SHY. X. SHX. Opcode is 9E. 3 bytes, 5 cycles. How do we describe this? How do we name this function? Hi, byte. Bitwise. And high address byte with register. I suppose. So we pass the register X and the absolute Y. Stupidly specific. So var high byte equals address shift by 8 and the result equals B register and high byte is high byte plus 1? It doesn't say plus 1 here. What does it do in here? 9E. So it is getting the address. Data equals X and the address plus 1. It is making a plus 1 in here. This one does not mention a plus 1. Which one do I believe? Are you in here? 9E. I don't see you. SX A SHX no. XAS no. Nothing. So the plus 1 happens before the AND, okay? And does it update any flag? No, it doesn't. Okay, that's cool. So this is memory, memwrite, address, and result. It's okay. But what if this is FF? High byte is bigger than I think this would be the right thing to do. Okay, one more less. Okay, no more scrolling. This is all the final 3 instructions. And Y register with high byte of target address. So this is the inverse. And Y register with the high byte of address plus 1 store the result in memory. So this is basically same function between 3, 5 S I A so it's written inverse. This is absolute X and takes register Y, and it makes the same function. M equals 3D Y and high X and so on. Why 3D? What is 3D in this? Well, whatever. Oh, this 3D is just some stupid meaning. I suppose it's just an equal. It's just how it writes the equal. Save. So this one is kind of unknown. Let's see what this one says. 8B. What does it say here about 8B? XAA. A equals X and they mediate and affects 0 and negative. And what does it do in here? 8B. A equal X, state 0 negative, reads the address, and then makes A and register A. What? It's strange. This does not match to this. Do we have an 8B here? A or magic and X and immediate. But what is magic? So seems to be different on different CPUs. No NES specifically. Do we have Nintendo manufacturer? No. I don't quite know which is the manufacturer of the NES CPU. Atari. Device tested in Commodore 64. I don't remember the real name of the NES CPU. I will choose not do it. If I don't know, I will not do it. When the time comes, I will implement it, I guess. And the last one is 9b. Stack equal A and X, address equals S and H. All of that in one instruction. Okay, it's quite straightforward. And the name is task in here. SHS stack high. I think there was another task already. And we have 9b in here. No. 9b. What name did it give? Task. Is there any other task? No? Okay. So let's use task, I guess. Bitwise and to register to tag, then and with high byte to memory. What the hell is this function name? And this takes two registers. So it will be saved into one of the registers. No? No, it is not saved. Func. This stupidly long name. P register 1, P register 2, P addressing mode. What is wrong with you? It doesn't like the new line. Okay. And like this. No. And like this. No. Well, whatever. So, stack pointer equals P register 1 value and P register 2 value. That is the first part. Then it's going to get the memory address. Getting the high byte as before. Oh, it's high byte plus 1? Oh yes, it's plus 1. And it's going to make bar and result. This is int. This is int. This is int. This is int. What else? Bar. Did I miss any other? This one. All of these. Right. Okay, seems to be all. Aha! Okay, awesome. Equals high byte and stack pointer. Are we doing it correct? Correct, and write it to the address. Memory, write mem, address, and result. And no changes in program counter. So with that, pause. And I guess I will put some breakpoint somewhere. Maybe in the break. CPU break. Quit. So if I pause, it did not pause. Do I have quit override? Why did it not run the breakpoint? What if I search for run? and put the breakpoint here. Okay. Finish it running everything. And now I want to see. Okay, we are in the CPU and I want to see the instruction set. 252 instructions. So there are a couple of ones that we skipped because I did not know how to do them. But let's just forget that. Because we are probably mistaken in a lot of other cases. It adding part. No. And I want to make this a little bigger so it matches in one line. Yes. Yes. No. Yes. Git commit and implement the rest of iLiga instructions. Most of the rest. Git push origin main. So there we go. So thanks a lot for passing by. We are done for today and we have made great progress, an important one, because we are now ready for the PPU chapter. See you next stream.